Hello everyone, and a very warm welcome to this webinar, where we're going to be looking at the subject of highly efficient, high temperature CO2 heat pumps. My name is James Chaplin, and I'm the Senior Product Manager responsible for Mitsubishi Electric's Applied product range. And on behalf of Mitsubishi Electric, I'd like to thank you for attending this session. We really hope that you find the content useful. This session will include an interactive presentation and feature 2 live polls. So we'd like to invite you to vote in them when the time comes. This will be followed by a Q&A session where I'll do my best to answer some of your questions. You can submit your questions throughout the presentation on the Zoom control portal. So let's get started with the first live poll. We'd really like to better understand our audience. I would ask if you could please tell us what your job role is. Are you a consultant, a contractor? Do you work in services, maintenance, or facilities? Are you a client or end user, or other? And so we'll leave that open for the next 10 seconds or so. Thank you. So that poll is now closed. Thank you. So I'd like to start by setting the context and introduce the drivers in the market that are influencing the change in the way that we use energy to create heat. So it was June 2019 when the UK government underlined its commitment to building on the UK's proud tradition of climate leadership by amending the Climate Change Act of 2008 to set a new target of achieving net zero greenhouse gas emissions by 2050. This world-leading target, which makes the UK the first major economy to legislate for net zero, is set to bring an end to our contribution to climate change in just 3 decades. However, to achieve net zero emissions, it is clear that we will need ambitious action in all sectors of the economy, supported by technological innovation, as well as robust policy frameworks. It is now 3 years since the Clean Growth Strategy was published, a document setting out ambitious policies and proposals for tackling climate change and driving clean growth right across the country. One of these proposals includes details of the government's commitment to support businesses to reduce their energy use by at least 20% by 2030. A reduction that has the potential to save the environment 22 megatons of equivalent CO2 emissions and business tenants up to £6 billion per year. As a follow-up to this detail, the Department for Business, Energy and Industrial Strategy closed a consultation in January 2020 to better understand how to support this reduction. Part of that consultation sees a preferred target trajectory of EPC-B for commercially leased property by 2030. But how can these ambitions be met? Business and industry are responsible for over a quarter of UK emissions, a significant proportion of which are created through businesses' demand for energy, with the majority of that energy used to heat the buildings they occupy. The decarbonisation of heat is arguably one of the most important factors to meet the targets to 2030. And we have seen independent bodies such as Ofgem and the Committee on Climate Change suggest that decarbonising the creation of heat via the electrification using heat pumps will play a key role in the coming decades. However, the drive towards a decarbonised future has been a focus for many years before government set our ambition into law. By studying the grid emission factor, shown by the blue line, we see that the UK has been very successful in decarbonising its electricity production, and there is a clear trend in the grid emission factors reflecting this shift away from fossil fuels. There is also ambition in the targets for the coming decades to reduce this figure further. In 2012, where carbon intensity for grid emissions peaks at approximately 530 grams of CO2 per kilowatt hour, the UK produced 40% of its electricity by burning coal. By comparison, in 2019, the carbon intensity had fallen to approximately 146 grams of CO2 per kilowatt hour, mainly due to a reduction of coal burning to only 2% of all generation, a reduction of 72% in only 7 years. In fact, the Low Carbon Economy Index by PwC, published in September 2019, shows that the UK has decarbonised its economy faster than any G20 country since the start of the 21st century. But how is this driving the electrification of heat? If we add the carbon intensity of a typical gas boiler with a COP of 0.98, we see that until 2017, gas-driven technologies were a cleaner source of heat creation. However, as the grid continues to decarbonise, it is clear that gas is not the future for heating as we move towards a net zero 2050. So why not just use direct electric? As has been stated by many industry bodies, reducing the strain on the national grid is an important ongoing task. One way to aid this is to use the electricity far more efficiently. Using electric directly for water heating could use more than 3 times as much over the same period. By adding the associated carbon emissions of heat pump across the same time period, we see a huge reduction in the carbon intensity. In fact, at the same point in late 2017, when direct electric became equal to gas, a heat pump could have enhanced the carbon savings by a further 69%. However, the success that we've seen over the past 7 years in decarbonising electricity has not been reflected in the way carbon emissions are assessed from different fuel types and technologies. The assessment method in Part L of the building regulations has not been updated since 2012, and so still gives preference to gas boiler technology to create heat. The recent proposed updates, released in SAP 10 and SAP 10.1, include figures for grid electricity which better reflect the carbon intensity factor at the time of publication. When adopted into Part L, these proposed changes will have significant impact on the choice of technology and primary fuel used and drive the electrification of heat across the whole country. However, even with the delay of regulation, it seems that major local authorities are taking it upon themselves to action change, and London are leading this campaign. London's Mayor, Sadiq Khan, has recently commissioned a report which details how heat pumps are the most important technology in the journey to a net zero future. The Mayor has set ambitious aims for London to be a net zero city by 2030 and to have the best air quality of any major city. The political will to deliver net zero carbon emissions in London has never been stronger. Reducing emissions from the creation of heat is London's biggest decarbonisation challenge. Natural gas, primarily used for space and water heating, accounts for 37% of London's greenhouse gas emissions. Conventional electric heating also contributes significantly to CO2 emissions and increases the peak demand on the local energy networks. The report goes on to state that London's carbon targets cannot be met unless there is a rapid transition towards low carbon solutions such as heat pumps. And it is estimated by the Carbon Trust that by the year 2030, there will be 120,000 heat pump installs every year just in London. The report does address the concern that heat pumps operate best at lower flow temperatures. However, as we will introduce, Mitsubishi Electric now have a highly efficient, high-temperature heat pump which provides a solution to inefficiencies at high flow temperatures. So now we understand more about the market trends driving us all to the electrification of heat. Let's introduce Mitsubishi Electric's QAHV product and CO2 heat pump technology. Specifically designed for commercial sanitary hot water applications where gas boiler, CHP, or electric water heating had been traditionally used, the QAHV provides a low-carbon solution for hospitals, hotels, leisure centres, student accommodation, and more. The QAHV is a 40 kilowatt air-sourced monoblock heat pump that uses CO2 as a refrigerant. Capable of flow temperatures from 55 to 90 degrees Celsius, the unit is highly efficient and capable of providing large delta Ts. The main value of the QAHV in the growth of the electrification of heat is its ability to show carbon savings against gas-driven technology when flow temperatures are high. Commercial heat pumps, such as Mitsubishi Electric's CAHV, have always been very efficient at providing LCHW for space heating, but struggle to show the same level of carbon saving when producing sanitary hot water at higher flow temperatures. Seasonal efficiencies of the QAHV producing sanitary hot water at 65 degrees Celsius have been calculated to be between 3.2 and 3.5, depending on the location, which when compared to a typical gas boiler can show carbon savings of more than 78%. A subject we'll expand on later. But why use CO2? CO2 as a gas makes up more than 390 parts per million, or 0.039% of volume of the Earth's atmosphere, one of the more significant gases. The ease by which it can be produced led to its early application in refrigeration in the mid-1800s, and it was subsequently applied widely in food refrigeration. The use of CO2 refrigeration in sea transport enabled the growth of the world fresh food market, and it reigned until the middle of the 1940s, when newly invented synthetic refrigerants became popular owing to their higher efficiencies and lower operating pressures. However, over the last 40 years, the environmental consequences of CFCs, HCFCs, and the realization of the global warming potential of HFCs have turned the focus back to naturally occurring refrigerants and HFOs. CO2 is a naturally occurring substance that is non-toxic, non-flammable, and environmentally friendly, with a global warming potential of 1 and an ozone depletion potential of 0. CO2 also has a low critical point of only 31 degrees at approximately 74 bar. So what does this low critical point mean for the operation? The critical point shown on this diagram is the point beyond which the gaseous and liquid phase of CO2 is the same density, and the CO2 vapor will not condense or change phase. CO2 in the QAHV operates above this critical point and can sometimes operate in what is defined as a transcritical cycle. This is where heat is rejected into the incoming water by cooling or desuperheating the CO2 vapor at supercritical pressure in a unique counterflow gas cooler. This cycle is why it is so important to maintain the return temperature to the QHV at as low a temperature as possible. If the return temperature into the gas cooler is high, then the ability to desuperheat the refrigerant is reduced, and so therefore is the capacity and COP. So let's take a closer look at what this looks like on a pH diagram. The diagram on this slide is describing the relationship between pressure, temperature, and enthalpy of CO2. The critical point is marked by the red cross. Point 1 on this graph is the point at which the refrigerant enters into the compressor. The effect of the inverter scroll compressor increases pressure from approximately 40 bar to 120 bar and increases temperature from approximately 10 degrees Celsius to 110 degrees Celsius. At the discharge of the compressor, the refrigerant has a huge amount of stored thermal energy. At point 2, this is when the refrigerant enters into the gas cooler. As an example, if the water inlet temperature to the gas cooler is 60 degrees, then the ability to desuperheat the discharge gas is significantly reduced. Here we see that the gas can only cool to a temperature of approximately 60 degrees. And this means that the delivered enthalpy through the heat exchange cycle between points 2 and 3 is only approximately 120 kilojoules per kilogram. At point 3, the refrigerant enters into the expansion valve where the pressure and temperature are both reduced before entering the evaporator at point 4. So now let's consider an inlet temperature of 10 degrees into the gas cooler. Again, at point 1, this is the point where the refrigerant enters to the compressor. Pressure increases from 40 bar to 120 bar, and temperature from approximately 10 degrees to 110 degrees. Point 2 again is when the refrigerant enters into the gas cooler. However, now the inlet water temperature to the heat exchanger is 10 degrees. And now we see that the gas cools all the way down to approximately 10 to 12 degrees Celsius. This means that the delivered enthalpy between points 2 and 3 through the heat exchange cycle is hugely increased to roughly 180 kilojoules per kilogram. At point 3 again, the refrigerant enters into the expansion valve where the pressure and temperature are both reduced before entering into the evaporator at point 4. This cycle is the unique feature of CO2 heat pumps and is the reason why such high temperatures can be achieved with large delta T's and with such high efficiencies. So now, having introduced the technology, let's take a deeper look at how we can design the system to make the most of these features. So the next few slides introduce some potential hydraulic arrangements and the basic control requirements. So as we've discussed, we need to maintain as low a return temperature condition as possible. When the return water temperature to the unit is higher than 29 degrees, we see an undesired capacity reduction and COP loss. Now, this can be acceptable in the later stages of a vessel heat-up cycle as the temperature in the vessel is increasing to the desired storage temperature, but it is certainly undesirable to be happening all of the time. We need to provide an indirect hydraulic solution. This is needed to prevent the heat exchanger in the QHV against poor or hard water quality, which could result in scaling and corrosion issues. And for projects where there is large peak usage, for example, a hotel or student accommodation, it would be suggested to have a store of potable hot water to meet the peak periods, like the example shown here. So here, the cold mains water is fed into the bottom of the storage vessel. Cold water is then drawn from the bottom of the vessel into the plate heat exchanger using a field supply pump, where it is then lifted to 65 degrees Celsius and supplied back into the top of the storage vessel. Hot water services are drawn from the top of the vessel, with the services return being pumped back into the middle of the vessel. The flow and temperature on the secondary side of the plate heat exchanger is monitored using the Mitsubishi Electric Q1SEK kit. The secondary side pump is controlled by the QHV using a 0 to 10 volt output to adjust flow rate to ensure the target flow temperature is met on the secondary side. The QHV is supplied with an integrated primary side variable speed pump, which is capable of achieving an external head of 77 kPa at 17 litres a minute. The QHV should be placed no more than 60 meters from the plate heat exchanger, and the primary circuit requires a minimum of 40 litres. The QHV controls the temperature in the vessel via 3 temperature sensors located in sensor pockets at the middle, top, and bottom of the vessel, shown here by T1, T2, and T3. The unit can then be commissioned to control the vessel temperature according to the target set point at any of these 3 positions. So for example, let's say we're targeting a set point of 65 degrees Celsius. The user may choose to turn the QHV off when sensor T2 reaches 65 degrees or more, and then turn the unit back on when T2 reads 60 degrees or less. Equally, the target could be set to turn off at T3 at 65 degrees or more, and back on at T2 when that reads 60 degrees or less. The system can in fact be commissioned to operate in 3 different control modes, each with different on-off conditions. For example, the user may wish to have different control points at different periods of the day or night. An alternative control method is to simply operate the unit with a target flow temperature, actioned by an external signal. This signal could be a non-voltage contact directly connected to the unit's board, or via a BEMS input over Modbus or BACnet. And again, for example, the temperature in the vessel here could be monitored by the BMS and trigger a signal when a particular condition is met, which then enables the QHV to run at its predefined and commissioned target flow temperature. That flow temperature could be anywhere between 55 and 90 degrees Celsius, and return off when the signal is stopped. Now, multiple QHV and multiple vessel arrangements can be achieved as per the schematic shown here. Each QHV requires its own dedicated plate heat exchanger, Q1SEK kit, and secondary side pump. The primary plant then serves the vessels using a common secondary side flow and return. The multiple vessels are connected in series using a bidirectional pipe between the vessels. You will note that the cold mains water is delivered into the bottom of the last vessel in the series, and the hot water services are delivered from the first vessel in the series. If 2 or more vessels are used in series, then the pump return should be plumbed into the bottom of the vessel before the last vessel in order to protect stratification in periods of low demand. When using 2 or more QAHVs, the preferred control method is to control the temperature in the vessels via 6 temperature sensors located and sensor pockets at the top, middle, and bottom of the first and last vessel. The unit can then be commissioned to control the vessel temperature according to the target set point at any of these 6 positions. Here, for example, let's say again we're targeting a set point of 65 degrees Celsius. The user may choose to turn the QHV to off when sensor T5 reads 65 degrees or more, and then turn the unit back on when sensor T4 reads 60 degrees or less, therefore assuming that the first vessel in the series is full of hot water. Again, the system can be commissioned to operate in 3 control modes, each with different on-off conditions. And it should be noted that up to 16 units can be controlled in a single control group. So now we understand how to maximize the benefits of this technology, let's take a closer look at the potential carbon savings. The QHV is highly efficient at high flow temperatures. In fact, depending on the location in the UK, the SCOP DHW can be as high as 3.5 when delivering a storage temperature of 65 degrees Celsius. The figure here shows the bin data for London, given the number of hours per year spent at each ambient temperature, and also the spot COP data for the QHV providing 65 degrees Celsius into a vessel at that corresponding temperature. By calculating the annual delivered energy and dividing by the annual input energy, we calculate the SCOP DHW, which for this example is 3.43. The result of this high seasonal efficiency is significant carbon savings. By using the figures for primary fuel from SAP 10.1, with mains gas being at 210 and grid electricity being 136 grams of CO2 per kilowatt hour, we find that the carbon intensity for QHV technology is just 40 grams of CO2 per kilowatt hour delivered. That means that right now, a huge 81% saving can be achieved against gas boiler technology with a COP of 0.98. But what about the future? What would happen over a typical product lifespan of 15 years? Using the grid emission projections supplied in the HM Green Book, we find that the average carbon intensity for grid electricity over the next 15 years is estimated to be 82 grams of CO2 per kilowatt hour. This means using a SCOP DHW of 3.43, the average projected carbon intensity for QAHV technology is estimated to be just 24 grams of CO2 per kilowatt hour delivered. The QHV is therefore able to demonstrate the best carbon savings when applied in an environment where the demand for sanitary hot water is high. We have focused on 4 key sectors, but of course these are not exclusive. The NHS and wider healthcare sector is a huge national consumer of sanitary hot water, and in 2009 the NHS produced their carbon reduction strategy for the coming decades. The key point to take from the document is that the NHS are looking to halve their carbon emissions between 2020 and 2030. Many of the operators in the hotel and leisure sector also have very ambitious targets to reduce their carbon emissions. Hilton, for example, are looking to reduce their carbon emissions by 32% across all of their managed and owned estate to 2030. So let's take a look at an example of exactly what these savings could potentially look like. Let's consider a typical 2 to 3 star hotel in London with 200 bedrooms. Using the guidance from CIBSE Guide G, we find that the daily demand of the hotel is approximately 22,800 litres of 65-degree water spread across a 24-hour period as shown in this graph. Here you can see the clear peaks in the morning and evening. CIBSE Guide G also recommends a vessel storage volume of 7,200 litres. So by using this daily demand figure of 22,800 litres, we can calculate the required kilowatt hours to move that amount of water from 10 degrees to 65 degrees, as shown in line 2 at a value of 1,456 kilowatt hours. Now, considering the seasonal efficiencies of QAHV and gas boilers to be 3.43 and 0.98 respectively, we can calculate the primary fuel used to generate the daily demand. These figures are 424 and 1,486 kilowatt hours for QAHV and gas boilers respectively. Now, by using the average carbon intensity for grid electricity and gas, and if we make the assumption that this will be a constant daily demand over the next 15 years, we find that the equivalent CO2 emissions for a gas boiler is 1,708 tonnes in the next 15 years, where the QAHV is just 190 tonnes, a huge saving of 89% over the lifespan of the product. This saving is equal to approximately 1,500 return flights from London to New York. And if you're currently exploring the government's £1 billion decarbonisation fund for public buildings, you'll be glad to hear that this represents a cost per tonne of approximately £38, well under the £500 per tonne required to qualify for funding. So let's close now by just looking at some of the additional benefits of QAHV and CO2 technology. So Pole 1 is the BREEAM credit that deals with the impact of refrigerants. The aim of this credit is to simply reduce the level of greenhouse gas emissions arising from the leakage of refrigerants from building systems. And there are 3 credits available, split into 2 assessment criteria. The first 2 credits can be allocated where the systems using refrigerants have direct life cycle CO2 equivalent emissions of less than 100 kilos per kilowatt cooling capacity, or if the refrigerant has a GWP less than 10. The other credit can be allocated if the unit is hermetically sealed or uses pump down. The QHV is able to gain all 3 credits as it is hermetically sealed and uses a refrigerant with a GWP of only 1. And finally, the QHV comes fully MNet ready, meaning that all of your other MNet ready Mitsubishi Electric equipment can be controlled from a single point. This includes City Multi VRF and HVRF, our E-Series chillers, and Mr. Slim splits. So in conclusion, the way we use fuel to create heat is changing rapidly. The government's ambitions and market shift towards the electrification of heat to reduce carbon emissions is only going to continue to grow over the coming decade. Mitsubishi Electric are ready to support the market with technological innovation and products that provide clear value in this journey to a net zero future. The QAHV fills the need for a highly efficient, high temperature heat pump that is able to show huge carbon savings now and in the future as the grid continues to decarbonize. Technologies such as QAHV allow Mitsubishi Electric to continue to contribute to society by reducing the impact of fossil fuel technologies and therefore create changes for the better. And so that brings us to our second poll of the session. We'd really like to know how well this information has increased your knowledge. And we'd kindly ask you to invite you to answer the following question. So how much has this webinar increased your knowledge of this area? Significantly, somewhat, or a little? And we'll leave that open for the next 10 seconds. Thank you. Okay, we're just going to end that one now. So that brings us on to the Q&A and the end of the presentation. So you can continue to ask questions on the Zoom control portal, on your control system. Let me just open it up and see if we've got any questions that we can answer. So we have one question from a nameless attendee, but they've asked if this product can be used for heating or just hot water. So in fact, the best application for this technology is sanitary hot water. As we walk through with the explanation of the need to have high delta T's and low inlet temperatures, that suits an application of almost semi-instantaneous hot water production. And so, in fact, this technology is very similar to our residential LED QUHZ product, which is again a CO2 heat pump system. And that system does generate both hot water and heating, but the way that system operates is via a thermal store method. So the outdoor unit keeps a thermal store at a defined temperature, and using that thermal store, there is an instantaneous hot water coil which generates domestic hot water at 43 degrees, and then there is a flow and return from the thermal store which can also be used in the dwelling for the LTHW. So what we see in commercial application is the need for a higher demand and a higher temperature, and thermal store type solutions can be tricky for that application. So in the way that it is applied with potable storage, it is best applied for sanitary hot water. So I hope that answers or helps to answer that question. Another question from Praveen. What is the maximum capacity of the QAHV that is available? Do you have a 200 kilowatt as a single unit? So we have one size module. It is a 40 kilowatt nominal system, and that's a 7 degree ambient temperature with a 65 degree flow temperature. but you can have up to 16 of those 40 kilowatt modules as a single control unit. So that would take you well over the 200 kilowatt that you would need there, and they can be packaged quite close together as well. So hopefully, Praveen, that helps to answer that question. Thank you very much. So Mark Ferris asked a question, many thanks for this. Is it fair to say that in practical terms that the highest return temperature is about 29 degrees, similar to the last question, I suppose? So in fact, Mark, the highest return temperature that the QAHV can allow is actually 63 degrees. So the unit won't go into a thermo off mode until it sees an inlet temperature of 63 degrees. So you are able to get the vessel temperature up to up to that temperature, so we can pasteurize that vessel every day to make sure that all of the water that's in the vessel has gone through that cycle. The reason to try and keep the inlet temperature below 29 degrees when we're in periods of high demand is so that we can really utilize that large delta T, which gives us a very high COP and a very good capacity output. I hope that helps to answer that question, Mark. Thanks very much. Okay, we'll just give a couple more minutes. So Simon's asked a question. Thank you, Simon. Some of our applications are large, 1.6 megawatts, and having 40 units isn't practical, of course. Are there any plans to upsize the unit, or is 40 kilowatts going to be the only available? So Simon, thank you for the question. We're always reviewing the demand for different size products in the market. So if we see as we start to launch this type of solution that there is applications that are needed in different sizes, or there's a real need for larger scale product, then it's certainly something that we would consider in the roadmap of development. Thank you for that question, Simon. Okay, so I think we're just about coming up to the end of our time slot. So it really just leaves me to say thank you very much for your time. Thank you for all the questions. I'm going to be live now on our virtual stand, so you can carry on asking questions via the app in the networking area. We can also ask questions in the discussion wall, so I think everybody else can then see the questions there for this session. And I guess that just really leaves me to say, I hope you found this session useful. Thank you very much for your time. If you need any further information and you're not available to come and talk after the session, please reach out to your Mitsubishi Electric account manager. And many thanks and all the best.